What makes a good nucleophile? Nucleophilicity is about electrons making a bond with some electrophile, some atom, usually a carbon atom. And when we talk about comparing nucleophilicities, we're usually talking about comparing rate constants, so which nucleophiles will react faster than others. In some ways, you can think of basicity as kind of a subset of nucleophilicity. Here, it's still electrons going to make a bond, but now it's electrons making a bond with a proton specifically, instead of just some electron-poor electrophile. And in 116, we learned we usually talk about basicity in terms of equilibrium, right? pKa. So kinetics really don't play into basicity very much, mostly because the proton is so small that steric effects don't play a role. But let's go into a little bit more detail about nucleophilicity and basicity. Here's a set of compounds that are good nucleophiles and strong bases. Generally speaking, things that are small and negatively charged. So hydroxide, methoxide, ethoxide, conjugate bases of alcohols, conjugate bases of amines, which are confusingly called amide or amides for some reason. But all of those small, negatively charged things, a lot of electron density, and really any carbanion, so anything with carbon with a negative charge. Remember, carbon doesn't like to have a negative charge. It's not electronegative. And so those electrons really want to go make a bond with anything. Two kinds of carbanions that are really useful to us are the ones that are stabilized by resonance with a carbonyl, and also sp3 anions or acetylates. So those are good nucleophiles and strong bases. We can also think of compounds that are good nucleophiles but weak bases. Generally speaking, these are polarizable electron clouds. They're spread out over probably a large atom, either by just the size of the atom or they're spread out by resonance, and they're often neutral. So in this case, the halides, iodide, bromide, chloride, those are all good nucleophiles and weak bases. Neutral amines are reactive as nucleophiles and a little basic but not strong bases. Sulfur compounds, and maybe this is obvious, but if we have S minus, it's going to be a stronger nucleophile than SH, but SH thiols are very good nucleophiles on their own. Other big atoms, selenium, phosphorus, generally speaking, big atoms are more nucleophilic than smaller atoms. And again, I'm talking about the lone pairs in phosphorus and selenium. Other nucleophiles where resonance kind of plays a role, carboxylates, cyanide, CN, just as deadly as you have heard, and azide, N3. It's a kind of a unique nucleophile. It's actually it's pretty unstable. It explodes. It's what's in your car's airbag. A little bit of electric shock runs through it to inflate the airbag when you need it. We use it in the lab somewhat. Again, these are really good nucleophiles. They're fantastic in SN2 reactions. Particularly sulfur compounds are fantastic in SN2 reactions, but they're not going to be good bases. So again, these classes are what you need to do to affect an SN2 reaction. So there are things that are poor nucleophiles but still strong bases. So these are not going to be good for an SN2 reaction. So generally what makes it a bad nucleophile is sterics. So a bulky base. Compounds that just have what I like to think of as antlers that get in the way of it attacking. So there are lots of bulky bases that synthetic chemists use. We will kind of focus on two of them, so you don't need to memorize a big list. So the one really common one is tert-butoxide. So you might see sodium tert-butoxide or potassium tert-butoxide. So here those methyl groups are making it harder for that oxygen to go make a bond to some electrophile. We also use LDA for this. LDA is lithium diisopropylamide. Again, I like to think of those little isopropyl group as antlers and just picture a big deer, a big buck trying to fit through a door, right? And the antlers are preventing it from getting in the door. And that's what keeps us safe from giant deer in our houses, right? That's why we have doors, in case you didn't realize, in case you didn't put those two things together. Okay, so again, these things have the charged atom, oxygen, nitrogen, just like the sort of green good nucleophile, good base, but steric effects are making it a worse nucleophile. So these are non-nucleophilic bases. Finally, let's look at some polar nucleophiles that are weak bases. So generally, these are going to have neutral electronegative atoms. So water is a great example. Water is a pretty weak nucleophile, and water is a pretty bad base too. Neutral oxygen in alcohols or carboxylic acids also fall into this category. You can see it says there it can take part in SN1 reactions. So we haven't studied SN1 reactions yet. That will come, I think, in week 8 or 9, just after the midterm. But for now, we can say if we've got neutral electronegative atoms, particularly neutral oxygen, it's not going to be a good nucleophile or a good base. And so it's certainly not going to be able to do SN2 by itself. You may have noticed in the last list, I never had fluoride anywhere, which seems like a weird omission, right? Fluoride itself is very small and very highly charged. So you would think it would be in that great nucleophile, great base section. It's actually not. So fluoride is a relatively weak base because it can hold its electrons relatively stably. But what about fluoride as a nucleophile? It's a little bit complicated because it actually depends on the solvent that you're looking at it in. We can define polar protic solvents as solvents that have a hydrogen bond donor. So water, methanol, ethanol, anything with an OH, anything with an NH. In polar protic solvents, fluoride's a bad nucleophile because the problem is it forms really, really strong ion-dipole interactions, kind of like hydrogen bonds, but remember fluoride's a dipole. And so these interactions are so strong that you kind of can't rip the solvent molecules away from the fluoride long enough for the fluoride to be able to go use those electrons to make a bond, right? So it's kind of like, when a celebrity can't get into a restaurant because there's so many hangers-on that are surrounding her at all times that she can't get in, or something like that. All right, so usually in these solvents, fluoride is a terrible nucleophile, and actually iodide and bromide are much, much better nucleophiles because they don't form such strong hydrogen bond like intermolecular forces. And so the bigger atoms are the better nucleophiles. If we think about nonpolar solvents like hexane or benzene or something like that, now you don't have the hydrogen bonding problem, but you're still not going to be able to use fluoride as a nucleophile because you're going to add fluoride as a salt, right? KF or sodium fluoride or whatever. And the fluoride will hold on to that other ion so tight that, again, it'll never be free to be a nucleophile. Okay, so there's some solvents where they are polar, but they do not have these strong hydrogen bond interactions. So we call those polar aprotic, and some examples are DMSO, dimethyl sulfoxide, and the DMF, dimethyl formamide. And what essentially is, if I drop KF in here, my potassium can kind of form strong interactions with oxygen. But steric hindrance actually prevents my fluoride from really getting that close to sulfur. And so it's kind of this cool thing where I'm solvating the cations. I'm sort of distracting my celebrities' fans, I guess. Maybe throwing food at them or just yelling gold. I don't know. I don't have much experience there. Anyways, the idea is that dimethyl sulfoxide and DMF will solvate cations, but it won't solvate anions, solvate being like stabilized around, etc. Won't solvate anions like fluoride. So iodide, bromide, chloride, these are good nucleophiles. Whether iodide is better than chloride or worse than chloride, that depends on the solvent system that you're using, because the stronger the intermolecular and ion dipole forces are, the weaker the nucleophile is, because the less chance it has to be a nucleophile. Fluoride is a terrible nucleophile in these polar protic solvents because of its strong interactions. But in some polar aprotic solvents like DMSO or DMF, fluoride's actually a pretty decent nucleophile.